In this, the third part of Optimisation series, we're going to have a look at storage, in particular how we might wish to store objects within memory. And we'll also then move on to briefly, in this one and in the next lecture, to have a look at temporary objects and how we can best deal with those. So storage, first of all, we'll start off with the question of whether or not we're going to store objects on a stack or in the heap. The nice thing about C++ is that we can choose where we wish to allocate data. And we've seen this before in terms of using the new keyword. Then we will be allocating a chunk of memory that resides on the heap. Delete keyword then to free it up. And other ones, if we just declare an instance automatically, or calling parameters inside a method or passing them in, they get to be stored on the stack. Languages like Java, we have slightly less control in as far as any of our objects automatically then get to live, to be allocated on the heap. In languages like C#, there's a bit more flexibility in terms of defining structs, which are value types, as opposed to classes. You can sort of have a bit more control over how you define and store data. But the general thing that we know is that anytime we allocate data on the heap, compared to allocation on the stack, it's a more expensive process, takes longer to do, and freeing up memory again takes longer to do. There's more of a management overhead. Whereas on the stack, it was quite easy to have a look at the number of bytes that need to be allocated, update the stack pointer, then to reserve that memory, and just to revert back to the old pointer by way of getting rid of it. So that would lend itself to saying that where possible, we should allocate data on the stack. As mentioned in some of the earlier talks, we need to be cautious about this because if we are returning that data and making use of the results, then the stack is not suited to data that will reside and live for a long time or is intended to be broadly accessible across a wide range of different objects. If we're considering where we actually allocate data, then this type of consideration also applies to the class data. You've got two examples here. We've got a class called foo. Foo makes use of some other class inside it, and in the instance in the top, the member property is being declared on the heap, and the class instance has a pointer to that. And the one at the bottom, we're then creating that object directly within that class, so it's embedded, it's packaged up within it. So that does make a difference. Makes a difference in terms of what it takes to copy or to move that object around, the size of it, the cost and the speed of which it can be allocated and deallocated. So generally speaking, the one at the top is a bit more flexible because we are simply maintaining a pointer then to this some other class. And in the future, some other class could be enriched through a class hierarchy to take on different types or different forms, and our foo class would still work. One on the bottom, because we are effectively hard coding that instance into the class, then we lose that flexibility, but we gain in terms of a bit by way of speed. So ultimately, what is better does depend upon how that object is likely to be used, accessed, the frequency with which it's going to be created or destroyed, alongside the flexibility that we will want to have in terms of how we access the class. Memory management itself, so let's just take a very brief delve down into looking at how the memory is structured inside the computer. But, there's a massive amount of stuff you could cover here, so this is the briefest of scratching of a surface. So when we think about memory, going back quite some time ago, really, I suppose back to the early 1990s. And before that, when you had a processor that was running at a couple of megahertz, generally, well, that was the clock speed of the actual processor, and memory speed was more or less the same as well. So everything was in sync. Getting into the 1990s, with the advances, the speed of the CPU outpaced then the speed of which sort of memory could conveniently keep up with. So you had processors running at 33, 63 megahertz, but memory was not able to run at that same speed, or at least not affordable memory was able to run at that speed. So that gets back to the point where caches started being introduced. And a cache is a piece of memory. It's generally a small piece of memory in comparison to the size of your main memory, but it's also faster in terms of being able to read and to access than main memory. So you've got this sort of small clump of very high performance and hence actually quite expensive memory that you can access, and the CPU can interact with at a higher frequency than it can in terms of main memory. Now that's good. That means it's faster than main memory. And the whole notion of a caching algorithm then is that in that small clump of very high performance, very fast memory, you put into that the data that you believe the CPU will want to access in the future. So there's a degree of speculation, and there's algorithms in terms of determining what it is you populate that cache with. So it is important to understand a little bit about how they work, and when we're writing our programs, it's very beneficial to us that we structure our programs in a way where the caching assumptions will be true, that the data that we want to access, the instructions that we want to be executed, they're likely to be stored within the cache and hence available to the CPU. Here's a rough structure in terms of the diagram and a bit at the bottom in terms of the actual performance difference to this. Now, there's no one structure here because different CPUs, different in terms of their caching structures. But this kind of captures a lot of the variability. So we've got our CPU core, sort of the orangey box down on the bottom right. And next to it, it has direct access to level 1 cache. And therein we can have an instruction cache and a data cache. So if we think about it, the machine instructions that we're executing, our program, it too resides in memory. And we want to bring those instructions in so that as the CPU is going through executing our program, it gets access to the next instruction nice and quickly. So the level 1 instruction cache generally holds the program. It operates on the assumption, as do most of the caching algorithms, that if you're executing one instruction in memory, the next instruction you want to execute is likely to be the one just after it in memory. So more of a sequential linear process through things. Now, obviously, if you have a for loop or a while loop, then you're iterating over a certain duration. If you have a branch or calling a method, then you're jumping to some other area in terms of the instructions. So it's anytime you're jumping about in memory, then you have a risk, I suppose, of being able to jump to an instruction that falls outside of the level 1 instruction cache and will then have to go and be picked up and pulled into the cache. Data cache, similar types of things. So this again assumes that if you access one piece of data, the next piece of data you want to access is likely to be next to it in memory. So if you're iterating through an array, that's why it's positioned altogether inside memory. So you also have lower levels, so level 2 cache, level 3 cache. So for example, in comparison to level 1, a level 2 cache is generally a bit bigger. It's a bit slower, but it's not as expensive in terms of being able to support that style of memory. Level 3 cache, again, a bit bigger than your level 2 cache, a bit more slower than your level 2 cache, and then you'll eventually work your way up to the main memory. Down at the very bottom, you can get a feel for just what performance difference between the caches is typical. These are not hard figures, they're just simply suggestive figures. So if you're dealing with a register, so this is something directly on the CPU core itself, you can access it in one cycle, the same cycle. It's available there to be accessed at the same clock speed effectively you're running at. If you do have to go out to hit level 1 cache, you're maybe sort of talking about 4 cycles or so. So this is 4 cycles where, well, depending on what other things the CPU can do, but it has to do other things for 4 cycles before that data is going to be available. Level 2 cache, maybe 10 CPU cycles to get information in. Level 3 cache, could be 75 cycles. If you're going out to main memory at the minute, you're into hundreds of cycles. So there is quite a high cost associated with getting data directly from main memory, and that's why we want to have it available in level 3, level 2, level 1 cache, so we can access it quite quickly. Now, what does this mean? It has lots of implications, but at a high level, what we should be thinking about is how we set out and how we structure data in memory, and try to do so in a way where if we think about how we're going to process that data, that the data that we need to process is all clumped together. So I'm going to show you an example on the left-hand side next to tortoise, which is a bit slow, and then a faster version next to the hare. So we're going to have well, look at the data structure over on the left-hand side. So it is a data structure, it's a struct. Inside that, we've got a couple of variables, one for an average, some for a standard deviation, and then we've got a clump of 100 items of data. So that data record takes some data, and alongside that has a few measurements, average, standard deviation. Underneath this, we've got process lots of data, or method. So we're assuming here that we're going to call this method, and we will be passing in a whole bunch of data records. So not just one, but a large number that we need to process. What happens in terms of the processing? Well, effectively, all we're doing there is we are iterating over the number of records that we have available. We're assuming that's some value somewhere. And we're adding up the average values for each record and then just dividing that at the end to get the net average of our data set. Now, if you think about this, in particular line 5, where we are accessing the average of the data record, and you imagine a whole array of data records set out in memory, and you think about where averages are going to be located in each of those cases. So if they are concurrently set out in memory next to one another, then one average, to get to the next one, you're going to have to jump over 101 other pieces of data, the floats, before you get to the next average. So that's reasonably big jumps through memory to access each of the average values. And in doing that, we will get to a point where we will rush through our level 1 cache, or level 2 cache, or level 3 cache more quickly. And there's more of a risk then that the algorithm that populating the caches won't be able to keep up, and eventually will then get out to be hitting main memory. If you wanted to improve this, structure over on the right hand side does so. So there we have broken up the data record into 2 records. We will have one struct containing a lot of raw data, and we have one struct containing our data stats, the average and the standard deviations. Now, that enables us to untangle these two things. A further utterly necessary assumption is that we assume that our data stats, in terms of the storage in memory, they're all stored next to each other. That we have, for example, an array of data stats, where array index 1 is the data stats for the first clump of data, array index 2 for the next, and so on as you go through. Given that setup then, it means we can change our process lots of data to pass in the data stats array, and iterating through that, we're basically just jumping over one float to get onto the next one. So it's much more, there's much less risk that we will be jumping through these things quickly and going outside of the content that we have within our level 1 cache. Much more likely then to be able to access it quicker. So those types of considerations about how we set out data for the algorithms that we're doing, and we do so in a way that we try to avoid jumping over large clumps of data, but keep everything together, maximizes the probability that it's going to be found within one of the fast caches, which again will improve the speed of our program. Temporary objects is the next item we're going to have a look at. So temporaries, when we talk about the notion of L and R values, so a temporary is going to be an R value. It's something that we as a programmer cannot refer to by name. It's created as a consequence of the processing that we're doing. So it's like a temporary, it's a part of the way there is then used and ultimately assigned to something that we're making use of, one of our L values. Now, it is important to understand the conditions under which temporary values might be generated, because there is a cost with creating and destroying these values depending on what the temporary value is, particularly if it's a class data. Now I say may be created because Compilers have a role to play here, and good compilers will put in lots of different tactics and strategies to try to minimize this. And we're going to get on to one known as the return value optimization, which is a fairly commonly used optimization that helps improve upon this. But we'll work up to that. So here we have a class, and I got down at the bottom we've got 3 examples of creating an instance of that class. And one of them definitely will not create a temporary object. The other 2 may create a temporary object, but in a good compiler they wouldn't. So we'll see this. Just have a look at the class first of all. So it's a rational number class. We are overloading, and we'll get onto that in the next slide. We're overloading the plus operator, so we can add 2 rational numbers together. We've got a sort of a default / parameterized constructor, 2 numerator denominator in terms of the member variables. Now at line 1, we are directly recreating this object. So R1 passing in a value of 10, that will create it directly with a value of 10 being passed in. No temporary objects created, definitely not. The second line, now you need to be cautious here, we're not using the new keyword in this particular one. So we're just saying rational R2 is equal to rational 100, perfectly fine. Now there's a risk there that a temporary object may be created. So a rational 100, that is calling the constructor. It will create a rational instance holding a value 100. We then have the equals. So we have the copy assignment constructor. So there's a risk in line 3 that we will create a temporary variable for rational 100, and we'll then call the R2's copy assignment constructor to copy the temporary value into R2, and we'll then face having to delete and get rid of the temporary object that we've created. A risk. Good compiler won't do that, but there is a risk of it. In line 4, so there we're doing R3 is equal to 100, but we'll see in the next slide, again, this can result in a temporary value because effectively there we might create a temporary object out of the 100 through basically calling the constructor implicitly, and then do the same copy assignment process. So let's have a look at this here. For any statement that we give, the compiler is going to try to execute it. It's going to try to do what we've asked it to do. And doing that, there's a number of things it's going to check to see can it do. So the compiler will merely determine if it can convert a specified type into expected type. Earlier on we've seen this in terms of integer conversion from bools to chars to ints. It will do it automatically implicitly. Similar type of thing can hold for classes as well. So if we do rational R and we do R is equal to 100. Now there we're in a quandary because likely then to have a temporary object being generated. So compiler checks for an assignment overloader accepting an int. So again, that will be the first thing it will check. There probably won't be an assignment overloader for an integer. Certainly we never defined one. So it checks that first of all, sees, okay, there's nothing I can call here that can take in an int. Next thing it's going to check then to see is there a constructor that accepts an int? If there is a constructor that accepts the int, then it can construct a temporary object and then use the copy assignment, the default copy assignment constructor, to copy across into R. Now in this case, for the class that we created, there is a constructor that does accept an integer. So you get the sequence of instructions at the bottom of the screen. So we have in line 1 a temporary rational. Now we're calling it temp here. It's the R value. We never get to see what it is actually called. We're constructing it, passing in a value of 100 and then the default parameter of 1. Then we're going to go to our R, which is our L value, and we're calling the copy assignment constructor, passing in our temporary variable. And then finally in line 4, now that we've constructed R, we can get rid of the temporary variable. So that's a cost. It's a hidden cost in terms of creating this. And it's one that unfortunately we've incurred based on how we've written our code. There is actually quite a nice way in C++ 11 of getting around that. It's known as the explicit keyword. And you can add this into any of the constructors in C++11. And what it basically says is that you're not allowed to call this implicitly. So it rules out anything other than an explicit, the programmer explicitly constructing an object using that parameter. So if you're in any way worried that, well, I wouldn't want anything else to be calling this implicitly, use the explicit keyword to rule that out. Now, we've got a similar thing we need to be concerned with in terms of return values, in terms of temporary objects being created. And we've seen examples in the last couple of slides for that. We have another one here. So we've line S1 being created with the string literal first, S2 string literal second, and line 3 we're creating S3 or third string. And in line, what should be 4 then, we're doing the S3 is equal to S1 plus S2. So we're concatenating the two strings and then assign them equal to S3. Now, if we think about that statement, so S3 is equal to S1 plus S2, how that gets to be executed is going to be as follows. Now, they'll check first of all for the string class, is there an overloaded plus operator? There is. So that enables you to concatenate two strings together, and it produces a third string. This is our temporary or hidden variable, or R value, that holds the concatenated values. So we're going to construct a temporary R value holding the concatenation, which will be first, second. We then go to the string class. Inside this we have an overloaded equals or copy assignment constructor. That constructor accepts in a string, so we'll pass in our temporary variable. We'll use that then to construct S3, and finally we'll get rid of the temporary R value. So again, reasonably, hopefully straight in terms of the series of steps that happens under the surface. Now, it's not a desirable series of steps because we don't want to be creating unnecessary values. You might go, well, why do we do that? The reason is reasonably straightforward. So if you think about when we were looking at the copy assignment constructor and defining it for a class, we have a method that's called on an instance, and the parameter to that method, the thing you have to pass in, is an instance of the class that you want to copy from. So we need something temporary that we can pass in to actually construct that string in the first place. Otherwise we can't do it. That's why we need it. Now, here's the key bit, and the bit down at the bottom, and we're going to return to it in the next talk. We're just going to introduce it here by way of a solution. If, and only if, S3 is a brand new string that has yet to be constructed. So this is the case of where we haven't yet constructed it, but it's there being constructed. If that is the case, then as opposed to creating a temporary variable and assigning it to a brand new thing that we are constructing, you can basically, instead of your temporary variable, just substitute that for S3. So you construct S3, in this case, directly. It's known as the return value optimization. And the next talk, we'll delve down into that in a little bit more detail. But it's going to be one of the key optimizations that the compiler will use to try to avoid unnecessary temporary object creation. From our point of view, we just need to be careful to understand the conditions under which it may be created, and to think about, is there anything obvious we can do to help avoid those conditions? Key takeaways in this, a couple of things. So specifically in terms of memory, it's useful to think about how the algorithms that we write will access and manipulate data. Also, as well as terms of how they will access and manipulate their instructions. And try to write and to structure our data so that we are accessing things that are all clumped together. We're not jumping wildly about and across memory. If we do that, it's very likely then our caching algorithms are not going to be able to offer us any performance enhancement. So do try to think about your algorithms from that perspective. It'll enable you to write ones that are considerably faster. For the temporary variables, and we're going to be looking at this in the next talk as well, there it's important to understand and be able to identify the conditions under which we might be creating temporary objects and try to avoid those. There'll be some things the compiler can do, we'll see in the next talk, that can help us out in terms of optimizing that process.